Hello, welcome to the new lecture of the course Transportation Network Analysis. So, in the last class, we were discussing about system optimization formulation, and we had seen the first order conditions for this optimization problem. We had also seen example for this. So, if you recall, the solution of the first order conditions of any optimization program is stationary points. It need not be the optimum solution. So, therefore, in order to ensure that a stationary point is also the optimal solution, we have to come up with additional conditions. We have seen some of the sufficiency conditions before. So, we will try to argue that whether the solution that is obtained from the first order conditions of system optimization, whether that is the global minimum or not. Okay. So, before that we will be making an assumption here on the link performance functions or the travel time functions here. The assumption is that the link performance functions are strictly convex, okay, and this is the typical way the link performance functions look like. So, assuming that these link performance functions are twice differentiable, this is then equivalent to saying that the second derivative of the link performance functions is positive for all the links. Okay. So, if you recall, before this we have seen two additional assumptions that we had made on the link performance functions. So, in the discussion of the user equilibrium case, we had discussed that the first assumption was that the travel time on any link is the function of the flow through that link only, and the rate of change of the travel time function with the flow at any point is positive. Okay. So, now this is the third assumption that we are making here related to the travel time functions or the link performance functions here. So, we will see how this will be useful while ensuring that the solution that is obtained from the system optimization first order conditions, that is also in fact the optimum solution. So, let us now argue that the solution of this system optimization program is unique. So, if you recall, we have been saying this, that there are some sufficiency conditions to ensure that a stationary point is a local minimum. So, for that we had seen some conditions before, and if we can kind of argue that there is a single local minimum for an optimization problem, then automatically that is also the global minimum. Okay. So, fortunately for optimization problems like user equilibrium and system optimization, it is possible to argue that there is a single minimum. Okay. So, then it is easier to argue that the solution that is obtained from the first order conditions is in fact the optimum solution. Okay. So, let us now argue that the solution that is obtained from the system optimization program is in fact unique. So, we have seen three kind of conditions that we need to ensure. These are sufficiency conditions to ensure that the solution of these first order conditions is in fact the optimum point, and it is a unique optimum, or in this case a unique minimum. First is that the objective function is strictly convex around any stationary point x star. Then the second one was it is the objective function is convex everywhere, and the third is that the feasible region is convex. Okay. So, we have to argue that these three conditions hold for system optimization formulation also, and if that is the case, then any stationary point that is found from the first order conditions will be the minimum, and it will be a unique minimum. Okay. So, out of these three, the last condition is easy to argue, because the constraints of the system optimization formulation are the same as the user equilibrium that we have seen before, and therefore, the feasible region is convex because the constraints of system optimization or the constraints of user equilibrium, they are linear constraints. Okay. So, that is why the feasible region that is found by those constraints is convex. So, this third condition is satisfied. Now, if we argue that the objective function is strictly convex everywhere, then we can argue that the system optimization is unique minimum in terms of the link flows. So, if we are able to argue that the objective function is strictly convex everywhere, automatically that will imply that the objective function is strictly convex around any stationary point x star, and also it will imply that the objective function is convex everywhere, right, because if a function is strictly convex, it is automatically convex. Okay. So, this also we have seen this before. So, let us argue that the objective function is strictly convex everywhere, and that will imply that the system optimization formulation has a unique minimum. Okay. And all of this uniqueness that we will be arguing will be in terms of link flows. So, if you recall, for user equilibrium also we had argued that the solution that is obtained is unique in terms of the link flows, but need not be unique in terms of the path flows. Okay. So, here also we will be arguing that this uniqueness is in terms of the link flows. Okay. So, in order to argue that the objective function is strictly convex everywhere, let us determine the Hessian of this objective function of system optimization formulation. So, we are representing the objective function of system optimization formulation by z tilde x. Okay. So, this is to differentiate it from the objective function of user equilibrium, which was getting represented by zx. Okay. Okay. Now, the objective function of system optimization formulation is the total system travel time. Okay. So, we want to minimize that. So, in order to determine the Hessian matrix of this objective function, let us first determine the first derivatives. Okay. And after that only we can determine the second derivatives. So, if we take the derivative of this objective function z tilde x with respect to the flow on link B here. So, by using chain rule, the first term that we will be getting will be this TBXB. Why? Because if assuming that out of these links here, so the summation is going through all the links. Okay. So, for that case, when A and B are the same here, so this A is the same as this B here. So, then when we will be taking the differentiation here, so first we will be differentiating with respect to xa. So, if A and B are the same, so derivative of xa with respect to xa will be the same, and it will be equal to 1 times this Txa. Okay. So, that is why we are getting this first term here. This is for the case when A and B are the same, and then the second term will be this xp times the derivative of this function with respect to xb. Okay. And now you can see that although there is a summation here, this is going through all the links that are there, but there are only two terms here, because for all the other links which are different from this link B here, all of those terms will be coming out to be 0 here after this partial differentiation. Why? Because you can see that if A is not the same as B, then since this travel time function of link A is the function of the flow through link A only, so therefore this function xa times Ta xa, so this is not a function of the flow through link B if A and B are different. Okay. So, that is why if you are taking partial derivative with respect to xb and A and B are not the same, so then all those terms are 0. Only when A and B are the same we get these two terms here. Okay. So, this is how we have determined the first order derivatives here. Now, since we have to determine the Hessian matrix, we need to differentiate it once again. Okay. Now, since we are here to determine the Hessian matrix, and this function z will be a function of the flows through several links. So, now we are differentiating this with the flow through link A here. Okay. Now, for the case when this B and A are the same, so then if you differentiate this with respect to xa, so this will be what? dTA by dxa, assuming again that A and B are the same. And for this term, when we are differentiating, again first we will take just derivative with respect to this. So, for that case we will just be getting this derivative plus xb times the second derivative with respect to this term. Okay. So, that is why we are getting this expression here. So, I would suggest that you do this exercise of obtaining the Hessian matrix. Okay. And for the case when b and a are not equal, all these terms are 0, because this whole term is only the function of the flow through link B. If A and B are not the same, so the partial derivative with respect to the flow on link A will be 0. So, that is why there is 0 here. Okay. Okay. So, now you can see here is that all the off diagonal terms of this Hessian matrix will be 0 because of this. Okay. When A and B are not the same. When A and B are the same, that is, we are focusing on the diagonal entries here. So, then this overall term here is positive. Why? Because the slope of the travel time functions or the link performance functions is positive, because we had made this assumption when we are discussing about user equilibrium, and this is also positive because we have assumed that the link performance functions are strictly convex. Okay. And again this flow x a will be greater than equal to 0. Okay. So, overall this term here, which is there in the diagonal matrix of the Hessian matrix here. So, this will be positive. So, therefore, this Hessian matrix is positive definite. Okay. So, if the Hessian matrix is positive definite, so that means that it is the function is strictly convex everywhere, the objective function, and if that is the case, then it is also strictly convex at any stationary point x star, and it is convex everywhere. So, therefore, given the fact that we have already established that the feasible region of system optimization formulation is convex, we can say that the solution, the stationary solution that is obtained for the system optimization program will be the optimum solution, and it will be unique. Okay. So, now let us take an example of the system optimization problem. So, this kind of network and travel time functions we have seen before. So, this T1, T2 we have seen this before, demand as 0.5, and this is the network we are focusing on here. So, this is a very simple network, it is just connected by two parallel links here, but now we want to determine the flows that we will get if they are getting distributed by system optimization. Okay. So, previously we had seen this example for the case when the flows were getting distributed based on user equilibrium. So, writing down the first order conditions for the system optimization program. So, since there are two links that are connecting this origin to destination here, so we have these two paths and each path is just consisting of one link here. So, that is why we have these two equations here in the first row. So, this F1 OD is the flow through the first path connecting O to D, C1 tilde OD is the marginal travel time on path 1 connecting O to D, and so on. Okay. And U tilde OD is the minimum marginal travel time on any path connecting OD pair OD. Okay. And so on. So, we can define these other variables also, and these are the conditions that this terms in the bracket here are greater than equal to 0, and the total flow sums to 0.5 as the travel demand is 0.5 and the path flows are non-negative. Okay. So, we need to use this information that the link performance functions are given by this before we can solve it. Okay. So, what we will be doing here is that we need to replace these marginal path travel time expressions by the using the expressions that we have for the travel times here. So, let us determine the marginal travel time for link A, which is this. So, it is Txa plus Xa times dTA by dxa. Okay. So, this will come out to be 2 plus x1 square, which is this travel time function, plus if you take the derivative of this with respect to x1, it will be 2x1 times x1. So, that is why we are getting 2 plus 3x1 square. Okay. And this is the marginal travel time on path 1 connecting this OD pair, because this path is only consisting of one link here. And similarly, we can determine the marginal travel time on the second path connecting O to D. Okay. And we need to replace the flow on the first path connecting O to D to be equal to the flow through the first link. Similarly, we need to make this change here. Okay. So once we substitute these into these equations here, then we will be able to get the solution of system optimization formulation. Okay. So now that we have focused on system optimization, let us do further discussion and differences between user equilibrium and system optimization. So the question is that, are there special cases where the user equilibrium and system optimization become identical? So when the congestion effects are ignored, both user equilibrium and system optimization programs produce identical results. Why is that? Because if suppose the travel time on any link A is equal to some constant T dash A, okay. So then if we determine what will be the expression for the objective function of the user equilibrium and the objective function of system optimization, both of them will come out to be the same, and that will be this summation xa times T dash A, where the summation is going through all the links. Okay. So when the travel time on any link is constant, that is, it is not varying with the flow through that link, that is, there is hardly any congestion effect. So then the result that you get for both user equilibrium and system optimization are identical. Okay. So the same flow will be optimal for user equilibrium case also and for system optimization also. However, when the congestion effects are considered, disregarding differences between user equilibrium and system optimization can lead to seemingly counterintuitive results. Okay. So we will be seeing some arguments to understand that why user equilibrium and system optimization can produce very different results and sometimes very surprising results. Okay. So we have seen an example before in the previous lecture to know the differences between user equilibrium and system optimization, but we will now be seeing a different aspect of the difference between these two optimization problems. So let us understand this through an example here. Suppose we have this network that is given here, it has 4 links, the travel time functions on these 4 links are given here, and there are 2 paths which are connecting this origin to destination. So the first path is this one, which is going through link 1 and then link 4, and the second path is going through link 3 and then to link 2. Okay. So we can determine the user equilibrium solution for this case, right. Now that we have also covered the first order conditions here, so there are multiple ways to solve this problem. Either we can write down the first order conditions and then we can solve it for the user equilibrium, or we can consider different cases and then also we can solve it. So suppose that you were to solve by taking different cases, so then first maybe you can make the assumptions that both of these 2 paths which are connecting O to D are getting used, that is, the flow is positive on both of them, and in that case one equation you will be getting is that the travel time on the first path is equal to the travel time on the second path. Another equation that you will be getting is that the flow on link 1 is equal to the flow on link 4. Similarly, another equation that you will be getting is that the flow through link 3 is equal to the flow on link 2, and also the sum of the flows on link 1 and 3 will be equal to the total demand equal to 6, which is given. Okay. So you have these 4 equations, you have 4 variables, you can solve them. So when you will be solving them, this is the solution you will be getting here. So in user equilibrium, the flows through all of these links is equal to 3 and the flow through all of the paths is equal to 3. Okay. Now that we know the flows in user equilibrium case, so we can determine the travel times through different links in user equilibrium. So that is very easy. So to determine the travel time to the first link here, what we just need to do is 50 plus this 3 that is there. So that is why we have 53 here. Similarly for the second link we have 53. For the third link it is 10 times 3, so this is 30 here and so on. Okay. And we can also determine what is the total system travel time on this network here in the user equilibrium case. So, just to recall, what is the expression for the total system travel time on the network? So, it is summation XAT, okay, where we are doing the summation through all the links A here. So, again that is not difficult to determine. So, for example, we need to multiply the flow through the first link, which is 3 times 53, plus the flow through the second link 3 times 53, plus again 3 times 30 plus 3 times 30. So, when you will be doing that, you will be getting this 498 units here. Okay. So, although we know that in system optimization this total system travel time is the objective function, but we can still determine what will be this value when we are distributing the flows based on user equilibrium. Okay. Now, let us make one change here. So, now let us construct this new link 5 here in this network, this link here. Okay, so the travel time of this new link is given here, and with this change there is now an additional path 3 which goes from origin O to destination D, which is to take link 3, then to link 5 and then to link 4, okay, this way. Okay. Now again for this case also we can determine the user equilibrium solution. Okay. So again whichever method you want to use to determine the user equilibrium solution, that is fine. So we can do that, and the flows that we will be getting in the user equilibrium solution is that these are the link flows that you get and these are the path flows that we get here. Okay. Just to remind you one more thing, if you are planning to solve this manually for finding the user equilibrium solution, so then what will be the equations that you will be getting? Assuming that all of the 3 paths are getting used here, that is the flow on all of the 3 paths is positive, one is that you can equate the travel times on all the 3 paths, that is one equation that you will be getting. Another equation that you will be getting is that the flow on link 1 plus the flow on link 3 should be equal to again the total demand 6. So, the total demand is not changing here, and other equation that you will be getting is that the sum of the flow on link 1 plus the sum of the flow on link 5 is equal to the sum is equal to the flow through link 4. Similarly, the flow through link 3 will be equal to the sum of the flow on link 5 and link 2. Okay. So, using like these kind of conditions and so on, we can determine this user equilibrium solution. Now, again for this case also we can determine the total system travel time on the network. Okay. So, again we need to do this summation XATA for all the links A. Okay. Now, when we do this, we find that the total system travel time on this case is 552 units. Okay. So, what did we see here is that the total system travel time has increased after the addition of the new link. It was previously 498 units when there was no link 5, and now it has increased to 552 here. So, this is slightly surprising in the sense that we constructed a new link or a new road, but the total system travel time has increased, that is the congestion is kind of in a way increased, which we did not want it to, because we have spent some money, we have spent some resources, and this network performance has in fact reduced. Okay. So, this seemingly counterintuitive result is called Braess paradox. Okay. Now, why is this the case here? So, why are we seeing this counterintuitive result here? The reason is that the flows are distributed based on user equilibrium. Okay. When we had determined these flows in both the examples, we were solving based on user equilibrium, where every traveler was minimizing his or her own travel time. Okay. And in user equilibrium, the individual choice of route is carried out without no consideration to its effect on other network users. So, when we are finding the solution of the user equilibrium, it is not necessary that we are minimizing the total system travel time of the network. Okay. So, if we have to minimize the total system travel time of the network, so then there is a separate optimization program for that called system optimization. Okay. So, from the optimization perspective, the new link was added with the intention to reduce the objective function of SO. Okay. However, the flows are distributed according to the user equilibrium objective function. Okay. So, that is why it is not surprising that why we are not seeing improvement in terms of the network performance or total system travel time, because the target of the flows that was getting distributed in both the case was to ensure that every traveler is minimizing his or her own travel time. Okay, we never wanted to target to minimize the total system travel time. Okay, but we were determining the value of total system travel time in the end in both the cases. So, the resulting flow pattern does not necessarily reduce the SO objective function. Okay, now the question is that what would have happened if the flows before and after the addition of the new link were assigned according to system optimization objective function. So, now we are making a change here. Suppose that we were solving these two cases again, but now we are distributing the flows based on system optimization, and then we are determining the value of the total system travel time. So, then the question is that will we again see, or is it possible to see increase in the total system travel time if we add a new link? Okay. So, the answer is that the total system travel time would have reduced or remained the same after the addition of the new link. The question is why? So, it is saying that total system travel time in this case, when we are distributing the flows based on SO, cannot increase after the addition of the new link. The reason is that the solution that offers a minimum total system travel time when there is no link is also a feasible solution for the case when new link is added. Okay. Why? Because one could assign 0 flow through the new link to obtain that solution. So, what it is saying is that whatever best solution that you get for the first case when link 5 was not present, that is also a feasible solution of the second case when link 5 is added, because you can always make the flow through link 5 to be 0. Okay, but vice versa is not true. So, whatever best you are able to achieve in the first network in terms of the system optimization, that you can also do in the second network also by making sure that the flow through link 5 is 0, but vice versa is not true. The best solution of the second case when link 5 is present may not be feasible for the first case. Okay, so that's why the total system travel time that you obtain after adding a new link can either stay the same or reduce. It cannot increase. Okay, so this is important. So, this Braess paradox underscores the importance of a careful and systematic analysis of investments in transportation networks. Some possible instances of Braess paradox in the real world have been observed. So, this is very important paradox, because the thing is that in terms of the real perspective, user equilibrium is more realistic than system optimization. So, people usually try to minimize their own travel time. No one wants to travel slightly larger to ensure that total system travel time is minimized, and therefore, the Braess paradox effects have been seen in the real world, because although the system planners want to minimize the total system travel time, but the travelers want to minimize their own travel time. Okay, so then these two targets may not align. Okay, and that is why this Braess paradox has been observed. Some examples is that in Germany, for example, in 1969, the traffic situation did not improve until a section of the newly built road was closed for traffic again. Okay, so there they constructed a newly built road, but they realized that the congestion has only worsened. Okay, it has not improved. So that's why they closed it again. Similarly, in 1990 in New York, it was observed that when they closed a particular road, the amount of congestion reduced. Okay. So, all of these are examples of Braess paradox. So, that is why it is important to analyze system optimization, user equilibrium, we should know its properties and so on. So, that is why we are doing all of this in this course here. So, with this we will be ending the discussion today. Thank you.